Bonjour tout le monde, bienvenue au séminaire en informatique cognitive. Le séminaire sera, ça sera présenté en anglais, mais vous pouvez poser des questions en anglais ou en français par chat. Moi, vous pouvez soit interrompre oralement avec votre micro au conférencier, ou vous pouvez mettre la question dans le chat et moi, je vais intervenir. Donc, Baptiste, je suis heureux d'accueillir Baptiste CARAMIAUX, qui est chercheur au CNRS à l'ISIR de l'Université de Sorbonne à Paris, dans le groupe de interaction humaine-machine. HCI, au fond, HCI, ça veut dire quoi, Baptiste?
Human-computer interaction.
C'est ça, d'accord. Okay. Il mène des recherches en interaction homme-machine, étudiant et concevant des interactions avec les algorithmes d'apprentissage automatique dans le contexte des arts, de la scène, de la santé et de la pédagogie. Il va présenter le contexte et la communauté de recherche travaillant sur ces thèmes à l'intersection entre l'interaction machine et l'intelligence artificielle. Il montrera des exemples de recherche où la démarche artistique est tantôt vue comme un outil pour réfléchir sur les technologies en tant qu'acteur culturel, tantôt que comme un outil pour inspirer la conception d'interactions riches et expressives. On va présenter des moyens concrets de concevoir des interactions avec des algorithmes d'apprentissage automatique à travers le concept de machine teaching. Et avec ça, je passe le volant à Baptiste CARAMIAUX. Bienvenue.
Merci beaucoup. So I switched to English and I'm going to share my screen. Alors. Okay, you should see my slide.
Yes.
Okay, thank you very much. So first, I would like to thank you, Stephen, for the invitation. And I'm really happy to attend this seminar on cognitive informatics. I'll try to bring my expertise within this field. And my expertise is in human-computer interaction at the intersection of machine learning. So as Stephen said, I'm part of the CNRS, research scientist at CNRS, and I'm part of the lab called ISIR, which stands for Intelligent System and Robotics. And so I will. So yeah, my group is called HCI Sorbonne Group. So we are a small group, quite new. We are 4 people, 4 permanent researchers, 2 postdocs, and 7 PhD students, and we are located there in Sorbonne University at the center of Paris. I would like to start maybe to present the domain of my research, because maybe it's not so familiar to everybody attending this seminar. The field is called human-computer interaction, and is usually defined as the discipline concerned with phenomena resulting from the interaction between humans and machines. This definition is very broad, and actually the domain and the discipline is very multidisciplinary, involving computer science, for instance, software engineering, signal processing, machine learning. Typically, we build systems. It involves psychology or cognitive sciences, neurosciences, and also social sciences and humanities, typically sociology, anthropology, in order to understand, once these systems are deployed in real world, how group of humans are interacting with them. So this is multidisciplinary. My background is more in applied mathematics, and then I've done a PhD in computer music. So I was in between computer science and music, and I was studying musical interaction. And then I've been also trained as postdoc in psychology. So just to tell you that I am myself a multidisciplinary researcher. If you're interested in knowing more, I will suggest this inaugural lecture at Collège de France by a colleague, Wendy Mackay, that was all this year. HCI, I've known several waves, so it's born in the 70s, and it has known several waves, like 3 usually. We define 3 waves. You will see why I'm presenting these waves. I think it's quite interesting and quite useful in order to understand what I will present later. So the first wave of HCI is usually what we call the human factors. It was in the 60s, 70s, and beginning of 80s is when HCI researchers were investigating how to build system or how to design system and interfaces, such as maybe speed up the achievement of a task. So it was mainly based on the study of human factors, from borrowing tools and methods from cognitive science and psychology. The second wave went with the deployment of these computing systems in workspaces used by groups of people. So researchers started to look at collaboration between humans while they were using computing systems. So how a computing system can be a medium also between several people in a workspace environment. And here comes sociologues, anthropologues that started to also look at more, human organization, human collaboration. And actually, it started like at Xero Spark in California. And that was between the 80s until 2000. And then usually we call the third wave after 2000, when computing systems starting to become personal and social, meaning mobile phones, smartphones. And there, people working in HCI started to look at not only human factors, not only productivity between people, but also user experience, emotions, contextualization, cultural aspect. Oh, there was a voice.
No, excusez, continue.
Okay, and so that involves more than, it involves other part of the human life and human organization. And I advise this paper if you're interested in these different waves by Susan Bodker. So my research is situated in this third wave mostly. Now, if we look at the link between, or the intersection between, or interaction between the two fields of AI, artificial intelligence, and HCI, there is this paper by Grudin, who started to look at or draw the history of these two fields. And that's quite interesting to see how maybe when one was like in his spring or summer, the other one was maybe in its winter. And there's many phases until maybe 2000, where it's not here because it was in 2009, but I would say that the deep learning breakthrough happening in 2011, 2012 brought the two fields, brought the spring in the two fields. And actually HCI researchers started to look a lot on AI systems when they were deployed in a real world situation. Typically, what we can see nowadays is when we look at where machine learning and artificial intelligence and data are used, we see that they are pervasive in most of the, not most, but like a big part of the computing systems that are developed in infrastructure, in analytics, either open source or in data structure and API. And what interests us as HCI researchers is also in looking at the application. And we see that this type of technology has been become ubiquitous in several types of applications, such as sales, marketing, automation, finance, security, and so on and so forth. And so this is important because it means that like the technological breakthrough brought a lot of incentives that created a lot of different applications that are used by people that are facing users. And this system embed machine learning or artificial intelligence systems. And maybe it has been deployed before understanding the interaction and understanding maybe the challenges and the issues that can rise when these systems are facing users. And this is even more, let's say, highlighted by the typical machine learning workflow that is used to develop and deploy such technology. Typically, the development of a machine learning system, a machine learning based system, relies on an algorithm with its input and output, and experts who are machine learning developers or machine learning researchers. And these experts, they are disconnected from the users usually. So the expert, they are developing the system by choosing parameters, choosing the models, the metrics, threshold, doing a lot of iteration, a lot of tests, and they receive some feedback, such as like the precision, recall, and maybe some visualization about the training and the performance of the system. And this is the development cycle. On the other hand, the user may not have an direct interaction on the system in order to tweak it, in order to adapt it. He might give feedback and data to the expert who will change eventually the system. And on the other side, maybe the expert will ask questions to the user in order to better understand how to change the system accordingly. And when the user has access to the system is usually through data, sometimes implicitly taken data in order to enrich the system in an opaque way, or black box way. And this part is usually what we call usage or testing, but it's not part of the development of this system. And this brings several problems that we have seen over the past years when deep learning or machine learning system has become ubiquitous in many applications, as I mentioned before. And this type of problems are, for instance, this typical workflow does not prevent biases because once the system is developed, it's deployed. So basically, it's a black box system which is deployed to the users. And the user doesn't have access and doesn't have any ways or agency on the auditing of the model. So it prevents system auditing by domain experts, for instance. It hinders machine learning literacy and democratization in the sense that once, if the user are facing already developed and rigid systems, they cannot understand its mechanics and they cannot then appropriate the system accordingly. Sometimes also reduce the robust deployment because development can be done through fixed benchmark and data set, and once it's deployed in the real world, it doesn't work as well as it was working during development. And of course, reduce transparency, which is linked to the bias, and there are actually more concerns than the ones that I've listed here. So to prevent this, there has been in the field of HCI and then the intersection of machine learning, where I also situate myself as a researcher, the idea to create interactive machine learning workflow where the user would be in direct interaction with the system. And this means that the user has agency on the system itself, so it can give data, feedback, but it can also select the model, select parameters, select the metrics and guidance, and so on. Select the metrics can mean, for instance, that the user can choose to use quantitative metrics like accuracy, precision, recall, the same type of accuracy that is usually used, but also qualitative accuracy or qualitative metrics or metrics on the type of error, for instance. And on the other side, as a feedback, the user can receive predictions, can receive rewards, same precision recall visualization, and so on. But the important thing here is that there is a simultaneous cycle of usage, testing, and development, which will make the system more adaptable, more personalizable, and then more robust sometimes, and less prone to biases. So this is the definition of interactive machine learning, and this is what will be about my talk. I will take a specific stance in this presentation. I would like to start by looking at maybe unconventionally to looking at artistic practice using this type of technology. In doing so, we'll highlight creative and creative ways to use this technology that will give us some insight on how maybe to rethink the design of this machine learning system, or the design of the interaction with machine learning system. So I will start by looking at artistic practice involving machine learning. And then I will present this idea of machine teaching. So going from machine learning to machine teaching. In order to implement this, I will present a tool that we developed with colleagues in order to compose interaction with machine learning. And finally, I will give some examples on how to assess maybe non-technical aspect of interaction between humans and machine learning, such as trust. So again, yeah, feel free to interrupt me if you have any questions during the talk. So I'll start by looking at and presenting quite quickly a recent study on looking at artistic practice with machine learning or artificial intelligence that we call explorers of unknown planets. In the recent years, I guess thanks to the breakthrough in deep learning, there has been also a creation of a movement in art, which is called AI art. That it's a group of artists that started to use machine learning and generative models based on deep learning in order to produce artistic works or to embed this type of technology in their practice in general. And for instance, this is a piece by Anna Riedler who trained a generative model. So here is a GAN, is a generative adversarial network, on a set of images that she took and annotated manually. And she tried to extract from this data set another story, a hidden story about these tulips and how it is linked to speculation. And so she based the training of a model on this data set, which is thousands of pictures that she annotated. And when she exposed the pieces, she exposes the data set, which is this, and also the output of the model. So this is one example of AI art. So I will give you two examples and then I will go to the study. And the second example is by Memo Akten, where he developed an installation where you could, so here in the picture you can see two screens, and then you can also see a light with a webcam that is capturing in real time what is put on the table. So this is the real-time webcam feed, which is given to a model, and the model in real time is actually generating generating images from the input feed. So it looks like this. So this is from Memo's website. You can have a look. He has many pieces. So on the left, you can see the webcam feed, and on the right, you can see the output of the model, and this is real time. So the model has been trained on seas, on images of seas and natural landscapes. And what is interesting here, why I'm showing this, is because in his work, Memo bring performativity in the interaction with the machine learning system, with the generative model, and this is very interesting. Okay. So I'll go on. So what we did, this is the study that is maybe more STS, like science and technology studies. We performed interviews with 5 artists who were Memo Octen, Jake Elwes, Mario Klingelman, Kyle McDonald, and Anna Riedler. And so we did semi-structured interviews, which is a kind of usual methods that we're using in HCI. And then on which we perform thematic analysis. So we interview them for an hour and a half about their use of artificial intelligence and machine learning in their practices. And we were asking questions about if this type of technology brought aesthetics, how much it was, how much they feel that they were in control of the technology, how much they feel that, or the ethical aspect related to the use of this technology, and so on. And so everything is described in this paper that will be presented actually in a month, but is already online if you would like to have more details. So we did this 5 interviews of this world-renowned artist, and from which we extract several findings. I will just give 2 examples of findings through quotes of the artist. So first, we found that what was really important in their use of machine learning, it's the notion of craft and crafting. And typically, I'm quoting Anna Riedler here. I actually think there are a lot of parallels between craft and art and between data and models. I think there are a couple of things, like the relationship between crafts, which is anonymous and less well regarded, its repetitive nature, and art. And when you see the datasets are anonymous and nobody talks about them. They're out there, and people are using them. And so what was really interesting here is, like, in a work, I mean, the work of Adler, but also the other artists, the notion of crafting the dataset, crafting the model, that was critical. And it's not necessarily based on maybe a conventional way to work with machine learning, using cross-validation, using metrics, but they had really this experiential skill, they acquire these experiential skills through crafting and through bricolage with this type of technology. We brought a lot of interesting insights for HCI researchers for how to maybe develop system that can be crafted rather than understood as a mathematical model. Another interesting findings is this notion of uncertainty, which is inherent to this type of technology. And in the work of the artist, uncertainty is meaning making. So if I'm taking a quote by Mario Klingelman, what he says is, it says that it reminds me of Francis Bacon. In fact, now I feel closer to him. There is this work with oil paint. He looks for accident. That's exactly the point. When you work with oil paint, it also has this certain behavior where everything mixes. So you can't deliberately push it in a certain direction. That's what he says. In working with it, there comes a time when a certain constellation is right. Then you stop, and you also have to decide, is this the best solution? Should I work on it? That's what I find in my work. Keep training, and you may destroy it entirely. So here it's, through the quote, Mario puts importance on the notion of accidents and the notion of uncertainty as a material for design, and as a characteristic that it needs to be taken explicitly and work with. And so while maybe in the conventional machine learning culture, uncertainty is usually something that is not something that you would like to have. Here in this type of system or in this type of interaction, it's something that is accepted, and it becomes a design material. So there are other findings that we found, but I will go on in my presentation, and just by discussing this first study. So why looking at the artistic practice is because it gives us insight on maybe how we think the interaction with machine learning, because from their practice we see that they are trying to shape machine learning technology. What it means is, like, typically what they develop is not a technical skill, is not a skill of the mathematics behind or the mechanics behind the model, but more an experiential skill that I think it's important also for user-facing machine learning system or AI-based system to have to have the possibility to acquire experiential skills, to be able to build a mental model and to predict what will be the outcome without necessarily knowing what is under the hood. Also, what is really important is the fact that machine learning is not only seen as a technical object, but also as a cultural object. So it's not only, again, a mathematical tool, but it's also something that conveys the culture, through the data that is actually using to be trained. But also it's a culture because it has been developed by a certain number of developers from certain company, and it also resonates in the mind of the person receiving the artwork. For instance, saying that, okay, this artwork has been using machine learning to be created, it changed the way we would perceive this artwork. And therefore, artists reinvent a narrative with this technology. So as I said, uncertainty and unpredictability become creative design materials to work with. And there's also a tension that arises from accepting the opacity of the model. So if they accept the opacity, they will accept the aesthetics conveyed by the model, but also resisting it because they have to be able to appropriate this technology. And the fact to resist it is something that is the most challenging for them. Okay, so I will not go on and show you something that we call machine teaching. So this is based on what I just said about the artistic practice using machine learning. We develop a series of projects with the students and collaborators about this idea of machine teaching. So now, if we put people, novices, in the role of teachers of these models, what happens, and how we can study what happens and what it brings us knowledge. So the machine teaching formalism is quite a recent concept in the field of HCI/machine learning. Is this idea that we, as humans, we have this ability to be able to explain a concept and to be able to teach to someone else a concept. So if we want to explain something to someone, maybe a kid, we'll try to, with words, if we see that this person doesn't really understand, we'll try to find another way to present it, maybe using metaphors, maybe using other mediums like drawings and so on. So as humans, we have this ability to teach and to transmit information. And the idea of machine teaching is these things of how we could leverage the teaching ability of humans in order to create interaction and interfaces that would help the machine learning system to be trained and to learn something, to learn rich concepts. This drawing, or this figure that there is on my slide, is from Gonzalo Ramos' paper from Microsoft, and where he kind of define and formalize the machine teaching concept. So we explored this idea of machine teaching in several projects, as I mentioned. I will present the first one, where we try to our objective was to build a tool for sound design, where the sound designer could, instead of exploring the interface of a typical VST, so a typical plugin in order to synthesize sound that is here on the right, through knobs and sliders, we wanted to build a system that could a sound designer could actually design the sounds just by preferences. So by guiding the system, by teaching it which set of parameters has the most meaning for the sound designer and which are not. So this is the work by Hugo Scurto during his PhD at IRCAM. So we wanted to develop a system supporting sound design and also study exploration strategies, so how people could explore through the system we developed. For this, behind the scene, we used a deep reinforcement learning system, which is an adaptation of Deep Tamer. I won't go into the details, but we used Deep Tamer, and basically we added in green ear, we added other signals, human-like signals that came from pilot studies. Typically, it's not only the reward saying, yes, I like or I dislike, but also changing the precision, the speed, having something that is like more than I like and I dislike, but like a super like or super dislike. And some more exploring actions and exploring state. And this came from, as I said, pilot studies that we did with the prototypes of the system. So I'll show a video of the system. Trying to lower down a bit the sound. So this is the interface. The type of sound it's making is this. It's pretty saturated. So I'm going forward. So we did a series of workshops to test the system that has been created. So with a professional sound designer. And the system looks like this. So here there is a timeline progressing, which is basically the system, the reinforcement learning system exploring. And here the lines is the interaction by the user. Here it's exploration. This means I dislike. This means I like. Then it's pause, and then we can come back to in the timeline to come back to a certain set of parameters that was interesting. And we could also demonstrate directly with knobs what we would like to have. Okay. So with this study, what we showed is that through this workshop, we showed that for sound designer, it was if we asked them to explore with this system, it was not necessarily evident for them. But when we were asking them to create something, like to have an objective, it became really useful tool, and useful in the sense that they could, when we have knobs, they had to enter in some kind of an analytic reasoning when they have to change the pitch and the loudness and so on. While here in this case, they would they say they could stay into the sound, so they could remain into the sound output, and not necessarily.
Can I interrupt you for something, because I have a
feeling,
sure.
Sure.
I have a feeling that there was something missing in the audio of what preceded. Were we just supposed to be hearing a buzzing sound, or was there something, or was there some content there as this was being modified?
It was more textural sounds, yeah. So I guess there was this buzzing sound.
So, and could you say a few words about describing what it is that we heard, so we know what it is that we should focus on?
Sure. So if I come back to what I showed, yeah, just lower down the sound again. So here, let me just lower down again. So this is a text. It's going to be a texture sound, which is synthesized by the interface I showed at the beginning, or that was in my slide, with a lot of knobs. And so we start with one set of parameters, and the system change the values of these parameters in real time. And this is the action of the reinforcement learning algorithm. So the action is just, I'm going to change slightly this parameter, then this parameter, and these parameters, which basically becomes a navigation in this 10-dimensional space. And each parameter, when the parameters change, it's another configuration of the sound synthesizer, which produces this textural sound, basically.
And what comes out is still just buzzing?
Yeah, it's this one. Oops. So what we had when you saw the yellow lines, it means that we explore another part of the space, in the 10-dimensional space. So normally the sound changed. I mean, it's still buzzing, but the timbre changed quite a lot. Sometimes it's pitched, sometimes it's not, sometimes it's really saturated, sometimes it's not. And that's the sound space that we were using.
It could be a psychophysical problem. I mean, we are not, as listening to that, we're not scaled to the level of nuance and of change that people who work on it are. And for us, it's not evident from these examples. Unlike, for example, the visual examples, it's not evident when you say a radical change. Our ears, which are not trained and not used to it, are not hearing a radical change. We're just hearing more buzzes.
Yeah, it makes sense. I mean, it's that's why also we did this. Yep, where are they? I'm just trying to find the people from. Yeah, that's what we first we work with professional sound designers who are used to work with this type of sound synthesizer. Plus, they were doing the workshop and the experiment with a headset. Like they have. They were not using the speakers from their computer, because that's true. Otherwise, I mean, first there were several in the room, so it would have been a nightmare. But also because they are used to work that way, so they are used to work with really high quality speakers, and they could listen to all the tiny changes in the sound. And that's true that it might not be the same for people that are not trained in that. Yeah.
It's certain that it's not the same for people who are not trained. But I have a feeling, I mean, the sound space is very, it's much more, even timbre space is much more richer than what we were sampling over there. And I wonder whether for demonstrations like this, it wouldn't be more intuitive to use much more dramatic modulations and not such subtle ones. By the way, there's a question here. Is there a link to this video of textural sound?
I don't understand the question.
Somebody, is there a hyperlink to this video?
Okay. No, but I think there is. But this was local on my computer, but I think it's online. Yeah.
Okay.
I can send the link. Yeah. I don't have it
here. If you tell me
here,
a keyword, I'll look for it while you're talking.
Yeah, basically, it's if you look at the title of the paper, this one,
exploring
designing
space. Okay.
Yeah, exactly. So this basically should be in the this is on the ACM digital library, and it should be a video associated with the paper with this example.
Okay, thank you.
Okay. Yeah, so that's an interesting question, because I work also with on musical timbre, like instrumental timbre, like flute and piano and so on. But the thing is, we don't have like this type of synthesizer, parameter-based synthesizer to produce this type of sound. So I guess what we wanted to do here is like to base our study on a tool that everybody uses it in the field of sound design. So this type of VST is a very classic in sound design, and everybody knew it when we did the workshops. Okay, let me continue if there is no other questions. Yeah, so another type of project using machine teaching, and this is to bring deep learning methods and deep learning algorithm to the general public, to novices. This is part of the thesis of Theo Sanchez. So here was the objective was first to identify teaching strategy adopted by non-experts. If you put a novice in front, for instance, an image classifier, what happens? And to study how non-expert will understand the machine's behavior. So this is the first paper that's investigated that. I would like to focus on one aspect of this research is about the machine learning uncertainty, because I mentioned it when I was presenting the work of artist practice. So the machine learning uncertainty is quite research in the machine learning and deep learning field. And we usually divide between two types of uncertainty. There is what we call the aleatoric uncertainty, which basically captures the ambiguity and the noise in the data. Typically is when we have two classes, for instance, cats and dogs, to be creative. What we have, the zone that is around the decision boundary here, it's where lies the ambiguity. And so, a model, if a new instance arises near this line, will have high aleatoric uncertainty. On the other hand, there is another type of uncertainty called epistemic uncertainty, which captures the novelty. So typically, if we have, like, again, a binary classifier trained on cats and dogs, and you give as input a panda, you should get a very high epistemic uncertainty in this case. So it's everything that doesn't know the model. So these two type of uncertainties are quite well documented, but at the same time, it's a reactive field, and we don't have the perfect method. But we use this method here as a way to guide machine teaching, to guide non-expert in order to train a classification method. So to do that, to compute the two types of uncertainty, we used two methods that I try to describe succinctly. For the ambiguity, to compute the ambiguity of a model, of a deep learning model, what we do, we basically duplicate the classifier. So here are 1, 2, 3 classifiers on top of a pre-trained model. And we look at their prediction in terms of likelihood over each classes. And if the entropy of these different classifiers is high, it means basically that each classifier is actually very certain, but about a different class. So maybe this one will predict cat, this one will predict dogs, and this one will predict panda, for instance. So they are all very confident, but they are all saying something different. It means that basically we have a high aleatoric uncertainty. For the epistemic, so for the novelty, a state-of-the-art method is actually to don't look at the classifier, but to look at at the end of the pre-trained model, at the features computed by the pre-trained model, so the feature of the input, and to build a simple probabilistic model. And for each new input, we compute the likelihood of this new input under this model. if it's pretty low, so the model doesn't explain what it sees as input, it means that we have a high novelty, so high epistemic uncertainty. So we explored that in this type of system, which is a bit a toy example, but it allows us to explore and to investigate the strategy by non-expert. People had to train a system to classify 3 types of cards: 9, queen, and king. So here is the interface of our system. So they could put in front of a webcam a playing card and label them in real time. So it creates an instance in the dataset. So here is the setup. You have here the webcam feed, and here the interface. So we'll come back to the. So yeah, so here we have our classes with the instances. Once we have like few already 3 data, like 1 queen and 2 9, the model is trained, and we already have an estimation of the uncertainty. So if the queen is as input, we have low epistemic uncertainty and low aleatoric uncertainty. And so we could I will go directly to the here. So typically, what happens is that if we put, well, if there is nothing, sorry, I'll try to, yeah. So if we have 9 and a 9 and a queen, it's basically something that both the 9 and the queen, the model knows both 9 and queen. So but it doesn't know the things, the 2 at the same time. So basically we have high ambiguity, but rather low novelty. But if we, sorry, I'm just jumping in the video, but it's okay. If we put a hand, for instance, like this, what happened is that, okay, the 9, the model knows the 9, but it doesn't know these things here, which is my hand. So it will say that there is a high novelty, so high epistemic uncertainty, but low aleatoric uncertainty. So what we did is that we tried to estimate with a different pre-trained model how our uncertainty methods manage to capture the novelty and the ambiguity in the dataset. We found that basically the pre-trained model plays a very important role, because if you change the pre-trained model, you can get very different data, very different results. For instance, here, this is the capacity of, so on the MNIST dataset, this is the capacity to differentiate between what is ambiguous and what is not. And we see that with the pre-trained model ResNet 50, we have a really good result, much better than the other 2. But if we change the dataset and use our cards dataset with the 9, the queen, and the king, all the results change. And now the best result is achieved using MobileNet. But then this is really dependent on how we basically annotate what is uncertain and what is ambiguous. Here you can see on the right the histogram given by the likelihoods, and we see that basically the uncertainty values, and basically what is classifiable, which means what is basically from the what is a 9, what is a queen and king, has a quite low uncertainty. What is ambiguous overlaps with the classifiable, and the novelty is on the top of the tail of the distribution. And basically what is classified or labeled as novel is when there is a hand, or when there is nothing, no cards, or when there is a card that is flipped. But the thing is, when we build this data set, we realize that what we label as novel and ambiguous is not so clear. And this is an ongoing research where we're trying to investigate more in detail what is perceived as novel and ambiguous, and what is this what is the gray zone between these two concepts, because they are not two distinct zones in the feature space, but there is a zone that is also overlapping. And this is an ongoing research. Okay, I think it's 4:20, so I will give you I will go on, but I'll try to go a bit faster on that.
It's okay. It's okay. Don't worry about it.
Okay, I don't remember until what time I have, so I don't know. I think I was counting on 1 hour, but I don't know. So
that's fine. Nobody uses up all their time. Go ahead.
Okay, so what I've shown you, like about the system using machine teaching, and so what we realize when we are doing this research in interactive machine learning is that there is a lack of tools in order to build this type of system. So as I mentioned in the very beginning of my presentation, is that the usual machine learning workflow is that an expert work with a machine learning system and is developing this tool. Usually it's using Python programming languages, and there are a series of tools in order to help developers to do that. But building an interactive application or interaction with this type of system requires tools that are not really explored and developed yet. So going back to what is interactive machine learning, in this survey by Dudley, they explore what are the elements of interactive machine learning. So the elements are: the user could have access to feature selection, so they could from the data set choose to select a certain number of features. They could select the model. Again, they could select if I want to use a KNN, a deep learning model, or so on. They could try to steer the model using different parameters from the interface. There is all about qualitative assessment. And this is typically using either accuracy confusion matrices, but also, as the artists do, is also using subjective qualitative assessment based on aesthetics, for instance. So, and at some points, there is also a termination assessment. This is when we consider that we should stop learning or we should stop training the model. And there is the transfer, so how we decide to package the model and deploy it. In interactive machine learning workflow, the end users should have access to all this or part of this. And what we did with a colleague, with Jules Françoise, is to build a toolkit that enable the development of such application. And what we call, it's called Marcel, and what we say is like it's more composing interactions with machine learning. And we started to develop this tool as a pedagogical tool, because we are teaching interactive machine learning at University Paris-Saclay, and we were lacking a tool also to transmit this, to do a machine learning education typically. And we started to develop this tool for that, and it quickly became very important for our own research and also for even innovations kind of project. So what software architecture will enable an interactive machine learning workflow? What we decided is just something based on components. So components can be inputs, something that captures some inputs, some elements that can be put on the interface, like button, sliders. Components can be data set. It can be models or predictions. And the idea is that all these components from the toolkit have as well an interface that can be instantiated on demand. So webcam can have an interface showing the webcam feed. We can capture instances with a button and so on. And the prediction can be visualized as a confidence plot, for instance. And the important thing is that we would like to have composable interface, which means that we, in projects where we develop a machine learning workflow, we might have different type of user, different stakeholders. We can have like domain experts. Let's say we have a project in the medical field. We might have like domain experts. We'll have the expertise of what they are seeing. For instance, if we deploy a skin cancer application, we might have end users that will just use this system. We might have people who would like to audit the system. So we need to have different interfaces for each of these stakeholders, let's say. So we need composable interface. So with the toolkit, we can compose the interface by changing the position of these different elements, but also just displaying some of them or not. Typically, it's a JavaScript based on JavaScript. So you can write your code and you have in real time the interface displayed on the right directly on your browser. This is important that is using JavaScript because it doesn't require you don't have to install anything. It's just run on the browser, on the mobile phone, on the computer, and quite easily in very few lines of code. Here, for instance, we have less than 100 lines of code. We built a really simple sketch-based classifier. So the use case of this system, we use it a lot in Theo Sanchez's PhD, and that his PhD was also an opportunity to implement and to develop this toolkit, where basically as a HCI researcher, we want to test and evaluate a certain interaction with machine learning, and we want to do it with the study participants that are usually remote. They are not necessarily coming to the lab, so we can deploy our application online and perform a remote study. So this is what happened also with the PhD of Theo. We built this sketch-based recognition system where people could associate sketches with label. For instance, here it's like this is a house, and they could train the system to recognize houses, cars, but also more abstract concepts such as love or literature. And this is a part of some workshops with the general public. And so through this, we develop this system, and thanks to the way it's architecture, the system is architecture thanks to Marcel, it's very easy to bring another stakeholder in the pipeline. And here, let's say a designer would like to take these experimental prototypes and create a more robust installation to be put in museums. So it's what it happens with this system. And now this sketch-based recognition system is part of 2 exhibitions in Nantes and Rennes in France. So why I'm mentioning this is because it's kind of useful to have these tools to be able not to change anything about the pipeline, the machine learning pipeline, but just, for instance, here in this case, just to change the layout. And we have exactly the same workflow, but just the layout changed, and it has been really cost efficient. A more complicated use case is when it involves domain experts, and this is an ongoing project at the hospital where we are deploying such a system for a recommendation in anesthesia, intubation and recommendation. And so what we have is like a domain expert with a surgeon, the user are the anesthetist, and we are the machine learning engineers and researchers. And we are basically all collaborating with only one pipeline, only one scripts, but really different interfaces. And for that, we have in Marcel an integration with Python. And so this is a kind of a demo where we have our Python script. Doesn't matter if you don't read the Python, it's just to say that the Python script communicates with the interface where you can choose the type of model that you have trained with your Python pipeline, usual Python pipeline, and just import it in your load the model in your application, and then it runs in real time, and you can just do like here's a classification of skin lesions. And here I'm, as a machine learning expert, I can explore the different models, I can test it, and once I'm happy, I can share it with the expert domain just by clicking one button. And on the other side, the domain expert could as well test it. So here is the share button, and then there is the expert having a different interface here that you can explore the capacity of the model. So here again, when we are talking about quality assessment, of course, what is important here is maybe the prediction that the system will do, but also the type of error, and the domain expert will be able to correct the prediction if needed. And if it's corrected, since the data and the model are shared between the machine learning expert and the domain expert, the model could be retrained automatically. Okay, that's the real goal of this tool is to be able to build build systems that are deployed in socio-technical systems that involve, well, this is in French, or involves users, involves researchers, involves researcher and developer, but also subject designers and maybe auditors. So through this tool, we could really engage and enable several stakeholders and study much more complex situation, real-world situation, involving also communication and collaboration between all these people around the interaction with the machine learning system. Okay, last but not least, 2 slides on because once we deployed this, I mean, I talk about the tools, and so I talk a lot about the workflows, and just to say that we are actually also looking at once these systems are basically deployed, we would like to assess other type of aspect that arise in the interaction with machine learning, and typically trust. So this is the PhD of Alexandra Vereshchak, and the context is that this idea of trustworthy AI or trustworthy machine learning is at the center of many international institutions. So in Europe, the European Commission has released a report 2 years ago. Different governments are also released some white papers, working reports, but also the private sector. So this is a big thing. And basically, Alexandra in her PhD tried to better understand how to evaluate trust, but how we could define trust and how we could measure and evaluate it. And so she did, as part of one aspect of her work, is to do this systematic survey of empirical methodology in the HCI community. And to do that, she basically extract different papers based on keywording, and then we did two paper selection. Maybe it doesn't matter that I enter in the details about the methodology. You can find everything in the paper. But something that is interesting is in her findings that first she really made a different distinction between trustworthy and trust, and basically she found that trust is not necessarily always defined in all the paper that she identified, and she proposed a definition based on the other definition, which is like trust is an attitude that an agent will achieve an individual's goals in a situation characterized by uncertainty and vulnerability. And so basically there are 3 key elements. There is vulnerability. So the people, the user or the stakeholder should be in a situation of vulnerability in order to trust to form. There should be a positive expectation in interaction with the system in order to have trust forming as well. And that trust is not a behavior, but an attitude, which means like behavioral behavioral measure doesn't really capture always trust. And basically, if we consider only two elements, for instance, vulnerability and positive expectation, what we measure is actually reliance, it's not trust. And the same, if we have like just the attitude and positive expectation, will be more something like confidence and not trust. And actually, this is hard to translate in French because we don't have all this distinction between the terminology. I didn't find them. And something. So this is one aspect of our findings, and I just present another one, but there is much more in the paper if you're interested. Is about the measures, and she found that, for instance, very few papers are actually contain question about because trust is often captured or measured with questionnaires, and really few are actually embedding or involving question related both to the willingness to accept vulnerability and positive expectations. And 1/3 of the papers are actually using behavioral measure of trust, which, as I mentioned, doesn't really capture trust always. And there is a lack of dynamic trust measure. So usually trust is assessed after one experimentation with the system, but it has been shown more in the psychology and cognitive science field that trust is a dynamic concept of that, and it can form, it can develop, it can be maintained, but it can be also damaged and sometimes hard to be repaired. And all this dynamic of trust is not really assessed in this concept or in this context, sorry, of interaction with the AI-based system. Okay, I would like just to conclude by trying to wrapping up what I've said is like what I wanted to show, to convey today is that but starting from artists that are imagining new workflows with enhancing user agency with machine learning system, we could imagine tools in order to develop this type of interaction. So the one I showed is actually community-based, is open source. I've shown that this type of system, this type of technology is more than a tool. It can be also a material and a cultural object. And also machine learning and socio-technical system involve critical non-technical challenges like trust, as I just mentioned. And on that, I would like to thank you, everybody, and thank you, my collaborators and students.
Thank you very much. Maybe you could unshare so that we can see one another. And I invite questions. I'll start it. Just press the reaction to indicate that you want to ask a question. In the meanwhile, I'll ask a few questions to start the ball rolling. I know that we have some artists and some musicians present, so it's not going to be just computer science questions. But I will ask a sort of an interface question. You spoke about uncertainty, and you spoke about aesthetics. I'm familiar with the relation between uncertainty and aesthetics in music and expectations, but how is it in general and in other fields?
When you say other fields, you mean other artistic
fields?
fields?
Other arts, if you like, or other creative uses.
Well, I guess what was common to all the interviews is that they are all embracing uncertainty, and that's something really important in the use of. Well, they are using these technologies not because it was fancy and hype, is because it's expressive and it has this level of unpredictability and uncertainty that makes the tool really interesting for them. So they have this feeling of of exploring unknown planets, as one of the artists was saying. To be able to create this uncertainty is actually fundamental to the use of this technology. So how they're using this is, I think, very personal, very idiosyncratic. Depends on each one of the artist aesthetics. Some of them are more into the control, very much like a virtuoso. Some others are really into exploration, and they leave free the uncertainty or the accidents happening. But for sure, that's a common denominator of these practices to embrace uncertainty.
Embrace. Okay.